Alright, let's go ahead and get started with Lecture 4. I know it says Lecture 5 here, but it's really supposed to be Lecture 4, the VSEPR theory, which this lecture discusses molecular shapes of molecules using Lewis dot structures. Alright, so essentially in this lecture we want to answer this question: how do you determine the molecular shape of a molecule for the Lewis dot structure? And so in order to be able to do this, you have to be able to draw a Lewis dot structure, and then from there you're going to predict the bond angles between what we call electron domains, and which will then result in the predicted structure or shape of the molecule. Alright, so what does VSEPR represent? Well, it stands for valence shell electron pair repulsion. And this theory basically tells us that the electrons that are in the valence shell are going to repel each other. They want to get as far away from each other as possible, as stated by this statement down here in the box. Electron pairs found in the outer energy level or valence shell of an atom repel each other and thus position themselves as far apart as possible. So here we're talking about both lone pairs of electrons and bonding pairs. And these bonding pairs and lone pairs want to be as far away from each other as possible, and so they're going to create these bond angles that allow them to give the furthest possible spacing. We also refer to lone pairs and bonding pairs as electron domains. And so you might want to think about electron domains. Right? So each lone pair consists of is considered an electron domain, and each bonding pair is considered an electron domain. And those electron domains then were going to position themselves as far apart as possible to create the geometrical structure of the molecule. Alright, on this slide there's some important points to write down. The first point here it's already in your notes. Again, we just stated again that they want to position the electron domains, or the valence shell atom in the valence shell atom, want to position themselves as far apart as possible. Right? But here are some other important points to put into your notes. We'll look at here is the repulsion applies to both bonding and non-bonding pairs of electrons, which we just talked about, and double and triple bonds are going to be considered as one domain. Alright, so single bonds are a domain, a triple bond is one domain, and a double bond is considered one domain, and then a lone pair of electrons is considered one electron domain. Alright, and all those want to be as far away from each other as possible. Alright, now this last statement here is really important, so make sure you have this in your note. What this statement is telling us is that electron domains that are lone pairs, because they're not bonded to anything, they have a higher concentration of charge, and so they need more space, and therefore they're going to repel bonding pair domains more. And so they're actually, if you had a lone pair of electrons and then two bonding pairs, or two bonding electron domains, it's going to cause those bonding pairs to squeeze closer together to allow more room for the non-bonding or the lone pairs of electrons. And I'll explain that as we look at shapes in particular. Alright, so let's get started with our shapes. The first shape we're going to look at is a linear structure. Now, if you look at the linear structure here, you can see that it has two domains. These are bonding domains because those are single bonds. So there are two electrons there in each one of these domains. And so these two domains want to be as far away from each other as possible. So what do you think is the largest angle these two domains can make to get as far away from each other? It would be 180 degrees. Right? So I'm going to actually up here at the top, right, 180 degree angle. An example would be this from a Lewis dot structure would be carbon dioxide. Carbon dioxide has double bonded oxygens to the carbon atom, and so therefore it has two electron domains. Remember, double bonds are considered its own domain. So those domains, since there's only two of them, they want to get 100. I should actually have two more. They want to get 180 degrees away from each other. Now, this makes up a good point. The geometrical structure is based upon the electron domains around the central atom. So we're just going to count those domains around the central atom. We're not even going to worry about the non-central atoms because they're not going to form the geometrical structures that we're looking at. Okay, let's look at one that has three electron domains. 1, 2, and 3. Three electron domain that are bonding, that is. So three electron bonding domains are going to form what is known as a trigonal planar. And what do you think is the largest angle for a trigonal planar? Three domains, how far can they get apart? It is 120 degree angles. So all of these make 120 degree angles. So what would be an example of this is something like BH, so boron trihydride, like that. Those are going to form 120 degree angles. So BH3. Of course, this is CO2 up here. Alright, now what would happen if we have three electron domains and one of those domains happens to be a lone pair of electrons? And that's what this represents, is two lone pairs of electrons. And so we have two bonding domains. There's our bonding domains. And then one domain that's an electron pair. Well, if you remember before, a lone pair of electrons needs more space than the bonding pairs. And because it needs more space, it's going to cause these bonding pairs here to actually squeeze together. They're going to kind of push together, and so it's going to actually make the bond angle smaller here. And so for this bent structure, the bond angle is going to be 117 degrees. So it's about 3 degrees smaller than a trigonal planar because of that lone pair. So I'm going to give you an example of one. Sulfur dioxide here. And then there's a couple lone pairs on the sulfur. And this is going to cause, these lone pairs up here are going to cause the bonding pairs to squeeze together to create a 117 degree angle and a bent structure. Alright? Okay, so let's go on. Now these next three are the most common geometrical structures found for molecules in nature. Tetrahedrals, trigonal pyramidals, and bent shape. Here's another bent shape. We'll talk about it. Now, each one of these now has 4 electron domains. We just got done with 3 electron domains. Now we have 4 electron domains. And so if I have something like the tetrahedral here that has 4 electron domains, the furthest these are going to get apart from each other is 109.5 degrees. 109.5 degree angles. An example would be like methane, and we often write it out like this. These are not 90 degree angles. They're really 109.5 degrees. So all tetrahedrals are that way, okay, with 4 bonding domains. Let's look at a trigonal pyramidal. It still has 4 domains, but one of those domains is now a lone pair of electrons. And so just like we saw earlier, a lone pair of electrons needs more space, and so it's going to cause these bonding domains, these 3 other bonding domains, to squeeze a little bit tighter together to create a smaller bond angle between them. And so the bond angle for a trigonal pyramidal is going to be 107 degrees. And a good example of this would be ammonia, NH3. So ammonia look like something like this, and you're going to have the lone pairs. And again, the angle here is 107 degrees for a trigonal pyramidal. Alright. Our next one is still, we got 4 domains, but now we have another lone pair. So now we got 2 lone pairs that are occurring here. And we create another bent structure. A good example of this would be like water, H2O. That's a terrible water. Let me erase that. Draw the little structure for water, H2O, like so. And so now these bonding domains here should squeeze even more closer together because we have now 2 lone pairs, or 2 domains that are lone pairs. And so the angle for here is going to be 105 degree angles for that bent structure. Alright, so far we've had linear structures with 2 domains. We've had trigonal planar and a bent structure with 3 domains. And now with 4 domains we have a tetrahedral, a trigonal pyramidal, and a bent shape. All of these shapes you must know. You must know their bond angles and be able to recognize them from their Lewis dot structures. Alright, so at this point, these are the structures that all of you need to know. If you're an SL student, these are it. If you're an HL student or a AP student, then you need to go on and learn these last structures here that are a little bit more advanced. So if you're an SL student, you're done with this lecture. If you're an HL student or an AP student, well, sorry to say, you're not done and you need to continue on learning these other ones, okay? So let's start out with a trigonal bipyramidal. The trigonal bipyramidal now has 5 domains. They're all bonding domains. And they're, I'm give you an example of like, say, PCl5. So PCl5, you have a phosphorus. Need more room. You got a phosphorus with a chlorine up here, and then you're going to have another chlorine out here, another chlorine, chlorine directly down, and then chlorine straight across like so. And the bond angles here are going to vary a little bit. This right here is going to be a 90-degree angle. This right here, that angle is 120-degree angles, right? And then, of course, from the chlorine to the chlorine, that's straight here. This one right here, that's going to be 180 degree angles. So, unfortunately, the trigonal bipyramidal is going to have 3 angles that you're going to have to know, be aware of. This one's a tough one, so practice it. Alright? Alright, our next one is a seesaw. Now, the seesaw has still 5 domains, but one of those domains is a lone pair. So just like we've seen with other lone pairs, they're going to cause a squishing of the other lone pairs. So let me give you an example of this one. Something like sulfur tetrafluoride. And you're going to have a sulfur, and you have a fluorine, and a fluorine, and another fluorine there, and another. You're going to have these lone pairs. And this really is going to look like a seesaw. And so the bond angles for this seesaw right here is going to be 117 degrees. Because of these lone pairs here, it's going to squish those bonds together. But the other two F's are still going to be at 180. Oops. Reset. 180 degree angles. All right. That's a seesaw. Now, T-shaped is you're going to have 5 bonding domains, but 2 of those domains are going to be lone pairs. And so you're going to create a structure like it's going to be this Cl, and then an F, and then an F, F, and these 2 lone pairs. Looks literally like a T-shaped, and the angles are going to be 90 degrees. So all the angles are 90 degrees. All 90 degrees on the T-shape there. Okay. And then the last one that is a 5 bonding domains. We're going to now have 3 lone pairs, and that's going to create a linear shape. Something like if we bond some iodines together, this is going to actually form a -1 ion. And you're going to have 3 lone pairs on that central atom, and that's going to create a linear or 180 degree shaped molecule. Alright, so that's all the possible shapes for a 5 domain or 5 domains around the central atom. Trigonal bipyramidal, seesaw, T-shaped, and linear. Alright, those are some challenging shapes, so you HL and AP students are going to have to learn those. Alright, the very last set of structures you have to know are all 6 electron domains. Okay, so there's 6 bonds around that central atom. The first one is an octahedral shape, and let me draw that out really quick. Octahedral, something like sulfur and a fluorine, 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 and fluorine, and another fluorine. The good deal here is that they're all 90 degree angles. Okay, in fact, is anytime you have 6 electron domains, all the angles are 90 degrees. So that's going to really help us out here. All right. So if we look at a square pyramid or pyramidal, it's got still the 6 electron domains, but one of them is a lone pair. And so it's going to look something like this, where we have an F, and F, 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 and F. And then you have those lone pairs there. And so that's going to be a square planar. And the angles on a square planar are also 90 degrees as well, all around them. Okay? Or a square pyramidal is what I meant, not a square planar. Sorry, square pyramidal. I'm off one. Alright, square planar. The square planar is actually going to have 6 domains, but 2 of them are lone pairs. And so that's going to be something like this. You have lone pairs there, and again 90-degree angles on those bonds. And that's what a square planar would look like. Okay, so this one would be like alright, so these are the structures you need to know and everything. So make sure you go back and learn all of these structures for class for the quiz. Go back and review the notes that you've taken and come prepared for all of this. And that will end this particular lecture.